So here we are going to have a discussion on hybrid parameters, and as we know that uh, we can draw a transistor uh, in a linear circuit configuration where we have an input port. This is the input port, and this is the output port. And we have two inputs, say this is I1 and this is V1, and two outputs, this is I2 and this is V2. All right, so this is a linear circuit. It's a transistor, it's a linear circuit. So we better understand here. We know what are the correlations, which couple is independent couple, and which couple is dependent couple. If I have to go back to the concept here, what we do is we have considered a linear circuit, right? Uh, Containing the linear elements in it. Now, in this circuit, input voltage and current are shown by V1 and I1, and the output voltage and current are shown by V2 and I2. That's clear. And currents at the terminals, they are considered as positive inwards. In the input and output voltages, V1 and V2 are considered positive from the upper to the lower terminal, right? So that's the case of convention that I'm trying to talk about here. Now, in this case, as I talked about hybrid parameters, what we have is I1 and this I1 and V2. They are, let's assume that they are independent variables, and V1 and I2, they are the dependent variables. That's what I will say is V1. V1 is the function of I1 and V2. So if I have to write down it in a mathematical form, I will write V1 is the function of I1 and V2. And similarly, I will write about I2 as the function of I1 and V2. Clear? Now, as this network is it's operated with AC signal. So when we say AC, that means there is change. So there are changes involved in these quantities, and changes can be they can be written mathematically by specifying or by writing the total differential of that function. So what will be the total differential for dV? For dV, it will be dV1 equal to dou V1 by dou I1, then dI1 plus dou V1 by dou V2 and dV2. Okay, this will be the total differential for this equation, and the total differential for this equation will be di2 equals it will be di2 by dou I1. So di1 plus dou I2 by dou V2 dV2. So we can replace these bracketed terms using some some equivalent terms for them. So talking about these equations, and now we understand that we have an AC equivalent circuit of the transistor to be developed. So we can take these partial derivatives uh, as constants because we are going to analyze the AC equivalent of this circuit. So these partial derivatives can be taken as constants, and these two equations can be boiled down to the equations. What should I write for that? Is okay, I have, so instead of dV1, I would like to write V1. Okay, so this dou V1 by dou I1, this is H11, and then I have I1, right? Okay, plus this dou V1 by dou V2, this is H12, and this is V2, and I2 here is I2 by I1, and that is H21 I1 plus this is I2 by V2. So this is H22 V2. All right. So we have this set of equations, and we can write down these equations in the form of a matrix as well. So as we understand the matrix formulation, we can write down V1 and I2 here, and this is equal to H11, then H12, then H21, then H22, and take a product with I1 and V2. Clear? It should be cleared. It should be clear. Yeah, this can be the matrix formulation of the above two equations that we have written down by assuming that these partial derivatives are acting as constants. So avoiding these partial derivatives, we have these equations, and we can write down these equations in matrix formulation, as you can see here. Now, moving forward, now these parameters that we have been talking here, this H11, H12, H21, H22, what they do, they relate the four variables of this two-port system by the equations. We have the equations here, so they are making a correlation between these two. These four variables that are involved in these equations, and we call them as hybrid parameters. So this H11, H12, H21, H22, they are called hybrid parameters. They're called hybrid parameters. Clear? Yeah, that should be clear. Now, we would like to define these hybrid parameters. We can define them by the original equations that we have in terms of their original partial derivatives. And we can create some condition by virtue of those conditions. We can have the value for all of these hybrid parameters. The first condition that we apply here is what we assume is if V2 is equal to 0, right? Now, if V2 is equal to 0, that means we have a short here. We have a short circuit input. Okay, so in this case, now if I take V2 equal to 0, what will I get for H11? H11 will be V1 by I1. Right? Now, this H11 is equal to V1 by I1. What we call it? We call it input impedance. All right. I would use the same condition, and I will be able to get H21. So in this case, I will get H21 equal to I2 by I1. Now what is it? This is called as forward current gain. Clear? So we have used the condition if V2 is equal to 0. So in this case, we have the short circuit input impedance, right? Now, taking another condition that I1 is equal to 0. Now, if I assume that I1 is equal to 0, I1 is equal to 0. What does it mean for I1 to be equal to 0? It means open circuit. Open circuit. Right? Now, if it means open circuit, so how would I come up from here? I will get H12 here. So H12 will be V1 by V2. This is V1 by V2. This is called as reverse voltage gain. Reverse voltage gain. Then finally, okay, I1 is 0, I will be able to calculate H22. This H22 is, what it will be? H22 will be I2 by V2. This is I2 by V2. Now this is called output admittance. Okay, so here this is impedance, so it must be measured in ohms. Here we have a ratio of the same physical quantity, it doesn't have any dimensions. Here we have the same physical quantity, it doesn't have any dimensions. And here we have admittance, that means we have ohm inverse. Right? So these set of equations that we have here, I would like to write them in a more symbolic way so that I'm able to connect them to the configuration of the transistors. When I have to analyze a transistor, I understand there can have three configurations of a transistor in which we can have it. So when I have to analyze, say, common emitter configuration, there I want these symbols to have some symbolic identity. So in order to go with that, what would I like to do here is for this H11, what is H11? That is input, whatever it is. So for H11, better is to go with the common emitter configuration completely here, because that's going to help us. Common emitter configuration. Okay, so for this H11, so first H11, 1 will refer to I, input, and this one will refer to E. So E is the condition for common emitter configuration. Now if we would have used common base configuration, so this H11 would have been replaced by HIB for the common base. If it would have been common collector, it would have been replaced by HIC. That would have been the case. So H11 is HIE for common emitter. What is this HIE? This is input impedance. This is input impedance. Now we have H12, okay? H12. So 1, 2. Okay, H12. Where is H12? Here is it. It is reverse voltage gain. So here we use R for reverse, and E for emitter, common emitter. Now what is this? This is reverse voltage gain. So in case of common emitter configuration, we can say that HRE is the representation of reverse voltage gain. And then we have what we have gone with 1 1 and 1 2. Now 2 1. Now what is 2 1? You can see here 2 1, it is F, forward current gain. So this is H21. H21 is for 2, it is HF, forward common emitter. So this is forward current gain. And finally, what we have? We have H22, H22, H22 equal to. So what is H22? How is it defined? It is it's output. So it is HOE. And this is output impedance. Okay, here I'll stop. So what we have done, we have written down the hybrid parameters, and then we have written down the symbolic presentation. We have defined these hybrid parameters like input impedance, output admittance, reverse voltage gain, forward current gain. And then we have taken a symbolic representation of these physical quantities for common emitter configuration. And you can do the same thing for common base configuration and for common collector configuration. And you can have a symbolic representation of H parameters for common base configuration and common collector configuration. So with this, I would like to stop here.